Welcome to Stories from the NNI. I'm Lisa Friedersdorf, Director of the National Nanotechnology Coordination Office. Today it's my pleasure to welcome Paul Alivisatos, Vice Chancellor for Research and Distinguished Professor of Nanoscience and Nanotechnology at the University of California, Berkeley. He is also the founding director of the Kavli Energy Nanoscience Institute. Paul, thank you so much for joining us today. To get us started, can you tell us a little bit about yourself and how you first got involved in nanotechnology?
Well, thank you for having me here today. I'm really looking forward to our conversation. When I was studying chemistry, physical chemistry, as a graduate student, I was studying how molecules transfer energy to solids. And so I was studying, on the one hand, the molecule, and on the other hand, the solid. And the languages seemed to be so different that people used to describe them. Molecules being described in a sort of physical chemistry language and the solids being described in a solid state physics language. And for me, I was very interested in how I could make those two connect and be one language. And when I later had the opportunity to be a candidate for a postdoc at Bell Laboratories, I met my mentor, Louis Bruce, and he was studying tiny crystals, which go between the molecular limit and the limit of a solid. And that was just such a beautiful question to me. It was exactly what I wanted to do. So I fell in love with that question, and that's how I ended up in the field.
I'd like to draw some attention to your institute. Can you tell us a little bit about it and why it was established and what you're trying to achieve?
I would very much like to tell you about the Energy Nanoscience Institute, which is sponsored by the Kavli Foundation. And really, the Institute is dedicated to the idea that when we think about how energy transforms from one form to another, in very, very many cases, those transformations at the very microscopic scale take place on a nanoscale, on the nanometer scale itself. And it turns out that there are many foundational principles that are not completely understood yet about how that occurs. It's such a curious thing because we have thermodynamics, which of course describes very well what happens if we have a large macroscopic system and energy is transforming from one kind to another. But when we look at individual energy transduction events that take place on the nanoscale, there are entirely new phenomena that occur because of two reasons. One is systems, when they're very tiny, can fluctuate a lot. So if we imagine a motor, for example, it won't operate the same on a very, very tiny scale as it will on a large scale because everything could be bouncing around because of the temperature. It's just completely different. And similarly, quantum phenomena come in, and therefore energy can follow different paths. And we see this all through nature. These kinds of phenomena, nature exploits them explicitly, but our technologies still don't completely know how to do that. And it's because we don't understand them at the deepest level. So the Energy Nanoscience Institute brings together a wonderful group of people from across all the disciplines of physics, chemistry, material science, biology, both at the Berkeley campus and as well at the Lawrence Berkeley National Lab. And together we have a wonderful opportunity to work on projects that try to uncover what are the rules or what are the principles according to which energy flows at this very tiny scale.
Can you share a little bit about some of the projects or the big scientific challenges that these scientists working together are trying to address?
Yes, certainly. We can take an example. I mentioned it very briefly. I'll give a couple of examples, but one would be, let's imagine that we do have a motor that's very, very tiny. We see many of those in biological systems. And those motors may not always go in one direction. Sometimes they may go forwards and sometimes backwards just because things are fluctuating and it can't always, if you don't want to spend a huge amount of energy and waste it, you have to kind of very close to the edge where it might go backwards or forwards. That's what nature does in many motors. So we have a group of colleagues who both study the biological motors but also try to make artificial ones out of nanoscale artificial components and try to see how they compare to each other and see what kind of behaviors they show. And part of it is, of course, trying to learn how to build things on that tiny scale the way nature does with the precision that nature can achieve. But part of it is also trying to have observational tools to watch energy flow on those tiny scales. So that's an example. The second one might be how heat flows. And of course, heat will flow in one direction. But if we have a system that's very, very tiny and we can engineer it very precisely, we might be able to make a system where heat flow in one direction proceeds at a different rate than the other, kind of like almost like a thermal diode. Finally, one, of course, question that has been part of chemistry research for a very long time, decades, is learning how to emulate photosynthesis, which, of course, all the primary events of photosynthesis happen on the nanoscale. And we're not quite yet able to replicate those in the laboratory. There's so many things that happen in natural photosynthesis that we don't yet have the facility to make things, or even, frankly, some aspects of the understanding that would be required to do that.
You mentioned that your institute brings together researchers from different disciplines. Can you share your thoughts on interdisciplinarity and collaboration and working across these traditional boundaries?
Sure, absolutely. And I think we can certainly use the analogy of language because we live in a global world that has so many languages. And if you learn one really well, but also a couple of additional ones, why then your understanding gets so much richer. You see things from many different perspectives, and you can interact with people with much greater facility. And that lets you do more things. And the exact same thing is true in the sciences of engineering, and it's certainly true on the nanoscale because physics, biology, chemistry, engineering, they all connect on this very tiny scale. And the ability to talk more than one of those languages is really powerful. And when people come together from across those areas, they can really interact in ways that are very fruitful. I think it is important to have a kind of a feeling, for me personally, at least I can say as a scientist, I feel that I have a very deep core love for chemistry. That's my home, but I spend a lot of effort to make sure that I can understand the other languages and have facility in them. And I find that helps me go back to chemistry and contribute to it in new ways. And it also helps me to interact with my colleagues and learn from them. And if there's one thing that we've learned from people who study the process of science, it's that teams with diverse backgrounds of all kinds, disciplinary, but others as well, are able to be more productive than those that are very monolithic in their approach.
I want to look at advances in nanoscience and nanotechnology, and it's an area that you've been involved in for a very long time. Looking back, what do you think are some of the most significant scientific achievements that have been made in this area?
Well, of course, there are so many. I'm going to call out kind of three examples. One of them is the development of basic scaling laws for how matter changes as a function of the size, whether it's melting or magnetization or structural transformations or quantum size effect. There are a number of kind of simple underlying models that kind of describe for us what we would expect to happen as we take a large piece of matter and make it smaller and smaller. And they're not always exactly right, but those, for me, having those in our minds is something that enables everybody to kind of think in a common way about some of the fundamental properties of matter on the tiny scale. A second has been the ability to make materials on the nanoscale. The level at which we can pattern and control things has advanced so remarkably, it's almost unrecognizable from what had been there. And what's so interesting about that one is how far we still fall short of what nature can do. And yet, compared to our abilities 30 years ago, the advances are just stunning. And maybe a third would be how much the observational tools continue to advance. This past few years, we've been involved in my research group in collaborations with colleagues across the world, identifying the position of every atom in a nanocrystal when no two nanocrystals are identical, using the spectacular advances that took place in cameras for electron microscopy that are able to have a dynamic range that was just completely out of the question even 10 years ago. There are just so many new tools that have been developed that allow us to see matter on the nanoscale. So to my mind, those are kind of a triad of things which form a kind of base for modern nanoscience.
With respect to the future directions or where you feel that nanoscience and nanotechnology will have an impact on world problems, where do you see opportunities?
Well, nanoscience is a fundamental discipline for how to control matter and energy on very, very small length scales. As a consequence, it can touch almost anything. And so I think this can be fairly simple. Health, climate, and information are the three areas where nanoscience is foundational to our ability to continue to have improvements in human life and the ability to have a healthy planet. In today's massive public health crisis of COVID-19, people may not be aware of the extent to which many, many nanotechnologies underlie the tools for understanding the virus and also for analyzing it, for preparing, filtering, separating, imaging. All of those things have within them nanomaterials control. And I think we'll see more and more examples where nanoscience-derived materials actually are part of all kinds of health-related sciences, whether they're public health or intervention health, prostheses, whatever. All of those things will be there. Even the understanding of the human brain, which of course does so many of its fundamental operations on the nanoscale, will ultimately, as we improve in our understanding of neuroscience, it will be based in part on nanoscience, and that may lead to the next giant breakthroughs in human health that will address issues of brain disease. When we look at climate change, the Energy Nanoscience Institute, as mentioned kind of earlier in our discussions, really studies how energy flows on the nanoscale, but those kinds of things are going to influence our future energy technologies, whether they're how we will perhaps capture carbon and remove it from the atmosphere, or we will have improved batteries which follow the scaling laws of nanoscience to be designed. All of those things will be really dependent in such critical ways on nanoscience. And of course, information technology, we're entering this era where quantum information and quantum computing will become important, increasingly important after the many wonderful breakthroughs in theory and in experiment that have been occurring. And the chain of that information flow will have in it the design of nanomaterials that use the principles of nanoscience.
What advice do you have for students that are interested in pursuing a career in nanoscience or nanotechnology?
I offered some language earlier, partly hoping that students would hear it, about wanting to learn language, thinking of scientific disciplines as languages, and being willing to learn more than one, having the energy and excitement about doing that, and also to remember to have the humility that there may be languages we don't know and we need to still learn them from our colleagues. That makes a good collaborator. If there's one thing I can say is that the way science is evolving, it's becoming far more collaborative. Being good at collaboration is a skill that I would advise young people to very much want to develop and to take advantage of. Maybe these days also to learn the wonderful new tools of data science, machine learning, artificial intelligence, and apply those to your area of discovery. Those are all things I'd encourage students to do.
I've really enjoyed the opportunity to chat with you today, Paul, and I appreciate your time. Do you have any closing thoughts that you would like to share with our listeners?
We're in the midst of a global public health crisis. And for so many people in this world, this is a very, very hard time. There are many people dying, and our economies are really being hit badly. And so it's a difficult period, and those difficulties are not equally distributed. They're really hurting people in ways that kind of amplify the inequality that we know is present in all of our societies. I do think together we'll work our way through it and get to the other side of it, but with a lot of difficulty. Our use of reason in science is going to be the path that helps us get out of it with the least damage to our society and with the prospects that after the crisis we can do better building for the future. So I think rededication to science and reason is something I'd encourage as much as I possibly can.
Thank you for joining us today for Stories from the NNI. If you would like to learn more about nanotechnology, please visit nano.gov or email us at info@nnco.nano.gov. And check back here for more stories.